Our first speaker this morning is Matthieu Wyart, who's a professor at EPFL, and he brings a unique perspective to overparameterized learning from theoretical physics. And he's here today to speak about unifying jamming, feature learning, and lazy training in deep networks. Take it away, Matthieu. Great to have you here.
Well, thank you. I'm really delighted to be here. And so far for me, it has been a great workshop. So really thanks to the organizer for putting all that together. So there are many words in the title that I need to explain further along the talk, but maybe I would start by just acknowledging my colleagues. So this work has been done with a set of very talented students and postdocs, and also with collaborators, Giulio Biroli at ENS, did some of the work with us, and also Clément Angler and his group at EPFL. So as you will see, yes, this is really a physicist approach to the question of overparameterization in deep learning. So maybe it's apparent in two ways. I mean, the first aspect is we will be seeking analogies between deep learning and physical systems like particles and sand, on the topic very dear to my heart. But also, I should emphasize that the methodology we use is also very much that of physics. So what we call theoretical arguments will not be theorems. What we demand, however, is that they are based on natural hypotheses and that they have predictive power. And then we really have to go and test those predictions empirically. So a lot of the discussion today contains also empirical facts and studies. We summarize those results, most of what I will be telling you about in this review that just came out in physics report. Okay, so can I get rid of this? Yes. So for most of this talk, I will be talking about classification. So to simplify matters, think about binary classification, cats and dogs. And as you know, deep learning is extremely good at doing this, but in itself, it is surprising because those data pictures lie in very large dimension. And if they had little structure, you could show that essentially you should not be able to learn to classify how to classify those objects. So the fact that deep learning works means that those data have a lot of structure, but what is the mathematical nature of this structure is still debated. And because of that, we also don't really know practical answer to question like how many data do we need to actually learn to separate cats and dogs, for example, even the order of magnitude of the number of data. So there is a common belief that deep learning works also because while you train networks, they actually do learn an interesting representation of the data, which maybe is more and more abstract as you go deeper and deeper into the network. So is it true? Is it true that you always learn features, or when does it occur and when it doesn't occur? And is it always beneficial or not? So I would like to touch those questions. Okay, so here's my setup. This is more to introduce my notations. So again, I will be thinking about binary classification. P will be the size of the training set. So data like pictures would be xi and yi would be the label. The output will be denoted F. W is the label for all the weights of the system. And other parameters that will be important here are the number of parameters in the networks, which I call N, and the width of the network. And in this talk, thinking about infinite width would be important. And so this would mean the number of parameters goes to infinity with H, while the depth is fixed. That's the limit we'll be playing with. And in most of the experiment measurements that I will show you, the nonlinear function acting on neurons would be a linear rectifier. So as you know, to train, we're going to build a loss function. And this loss function is made of a sum of terms that describe how well you fit data I. Here in this talk, I will actually focus on hinge losses. And hinge losses are like that. So the loss becomes 0 if you fit your data by a margin 1, if f times yi is larger than 1. If it's not the case, if the margin is smaller, then you start to pay some cost, which could be, for example, quadratic in the distance to the margin or linear. So why do we actually use the hinge loss? Well, it's both for a practical and a conceptual reason. The practical reason is that if you use a loss like that, when you are in the overparameterized regime, at some point in time, the loss really hits 0 and the dynamics stops. If you use the cross entropy loss, then the dynamics goes on forever and you need to add a parameter, which is a stopping time. So we just don't like to do that. And another practical reason is that if you look at performance on state-of-the-art architecture with those hinge losses or cross entropy, it's essentially the same. There's also a conceptual reason why we like this hinge loss, is that for the hinge loss, bringing the loss to 0 is equivalent to solving a set of constraints, which are for each data, f times yi needs to be larger than the margin, say 1. And problem of satisfiability have a long history in physics and computer science, and actually Florent yesterday mentioned that, for example, coloring problems and KSAT and so on. What's specific of the problem here, which also occurs in other problems in physics, is that the degrees of freedom, the weights, are continuous variables, not discrete. Okay, so I will come back to that. Yes. And then when you train, what you do is that, and it will be very important for this talk, initially you randomly initialize the weights. So you take the weights to be some random, to have some random values, and then you do gradient descent or stochastic gradient descent. And again, in most of the talk, when I show empirical data, we try to stay close to gradient descent, except when it's very complicated architecture where we do stochastic gradient descent or things like that. But then it immediately raises a question. You do some gradient descent in the loss function, which lie in very large dimension and has no reason to be convex. So why don't you get stuck in, bad minima of this loss? So that has the question, what is the geometry of this loss landscape? And what was proposed early on is that maybe this geometry is very similar to the one we find in some physical problems, where it's glassy and it's only made of an exponential number of minima, and then you will really get stuck. But actually, empirical measurement in the last years and also mathematical papers show that actually it's not the case when you have plenty, when you're really overparameterized, when you have plenty of parameters. And then what is found is that once you find a minima of the loss, it has many flat directions. So our contribution to that was to argue that actually there is a sharp transition between an underparameterized and an overparameterized phase, where you go from a glassy landscape to a landscape that's not glassy. And I will not review it in detail, but I just want to mention it in 2 slides. So it's based on an analogy with physical systems. And the physical systems that have been studied a lot in the last 15 years are just interacting particles. So think about those blue disk as repulsive, finite range, elastic particles, say. And the analogy between the system of particle and deep net is as follows. So in both cases, you have continuous variables. So for the particle problem, it's the position of the particles. And for the deep learning problem, it's the weights. Those are the weights. Then it's a minimizer. What are you trying to minimize? So for the particle system, it's not a loss, but it's the total energy. But just like deep learning, it's a sum of many terms, which are the interaction potential between pairs. And so at the end of the day, if you want to bring the energy of the system of particle to 0, you also need to satisfy a given set of constraints. For every pair of particle, their distance needs to be larger than the particle diameter. Okay, so just to make a long story short, and just to tell you what the 15 years of research on that, one of their conclusions is that you have a phase transition in those problems, right? You put randomly particles in a box at random position, and then you do a gradient descent. What do you observe? Well, you have a phase transition, which is controlled by density or packing fraction phi. If the density is low, you will manage to bring the energy to 0. And then the system is not glassy, you can move things around and you have many flat directions. But if the density is large and you quench, you look for a minimum, then you're stuck in a bad minima. And you have a phase transition between the two where properties are singular. For example, the Hessian, the spectrum of the Hessian is very special right at that point, or near that point. What was also understood is that you have different universality classes. So it's the other universality class can be represented, for example, by non-spherical particles like ellipses. They also jam, but their jamming transition is different. For example, if you look at the Hessian close to or at the jamming transition, it is actually different qualitatively from spheres. So actually, there is some interesting paper by Silvio Franz and Giorgio Parisi who actually realized the connection between, they were interested in the sphere problem, and they show a connection with the perceptron. Some exponents that enter in the perceptron also take place for spheres. And to do that, they actually use replica methods that Florent talked about also yesterday. But those methods, you cannot actually use them for deep learning. Currently, we don't know how to use them. So what we did instead is to use other kind of theoretical arguments that were developed in the context of this jamming transition. And it's essentially based on stability argument on demanding that the Hessian is positive definite. And so we obtained those two results. The key result is that, yes, there should be a sharp jamming transition in deep learning too, and it falls in the universality class of ellipses. And that led us to make prediction on the Hessian close to the transition, and we could actually check that it was correct. Another aspect is that what we find is that if the number of parameters is larger than some number C0 times the size of the training set, the system cannot jam. So the weakness of this argument is that C0, we cannot bound it theoretically, we measure it at posteriori. And so those ideas, which I'm sorry, I cannot really enter in any details. I would rather focus the talk on generalization error and performance. You can test them, and that's what we've done, for example, for MNIST, use those digits. Here, what you see is this little phase diagram is actually for a fully connected net of depth 4. And so what you do is that you, in this phase diagram, to obtain it, you fix the size of the training set. It could be maximum 60,000 data, but you could also take it to be smaller. And once you fix it, you modify the complexity of your net by increasing its width. And that means increasing the number of parameters. It means going up in this phase diagram. And so what we found is that, yes, if you don't have enough parameters, you cannot fit your data. And the loss, this hinge loss, is strictly larger than 0. But if you have enough parameter, you do manage to bring the loss strictly to 0. And then we could study what happens close, the phase transition that happens close to this line here, in particular the Hessian and other properties. Okay, so there is this phase transition. And in terms of bad minima, it just means something at the end, which is very simple, which is to avoid those bad minima, just crank up the number of fitting parameters, and you will actually manage to fit your data. But then that led us to the question of generalization. Okay, you can crank up the number of parameters, but then you will overfit. And like Florent, we also are very familiar with this story of Fermi telling about the elephant and the 5 parameters. And so we're expecting a U curve like that. And so to test that, what we did is to go along this phase diagram, choose a given, size of the training set, and study what happens when you train networks of more or larger and larger width. And so we went along the 3 arrows in the phase diagram. And then to measure the performance, we just measure the test error on a test set. And then we did obtain, to our surprise, these curves that are now called double descent. So where you would think that it may work the best at the jamming transition, it's actually the worst. It has this peak. And then it has the second descent here. And so, in fact, those results were observed 1 year earlier for regression in shallow networks. So we saw it for classification in deeper network, fully connected, and then CNN. And Belkin had this very nice paper where he also see that in other machine learning problem and where he coined it this double descent. So there are two interesting asymptotic behavior. One is this peak here. Essentially, it corresponds to a divergence of your predictor. That was already discussed by Advani and Sachs. For classification, we think that the exponent that characterizes this divergence is actually different from regression. But today, I want to not to enter in this discussion. I would rather like to focus on the second descent. Maybe that was the most puzzling to us. So it's a regime where you fit perfectly the data, and still it's good to increase the number of fitting parameters. How come is it so? Actually, this question was already there for several years in the literature and studied by scientists like Srebro and coworkers. And they came up with this nice idea of implicit regularization. But here we would like to have an understanding of this problem, which is also quantitative. For example, how fast, which exponent describes how those curves reach their asymptote value. And we see that you need to have immense number of parameters to improve the performance. Can we have simple operations that get us the same performance with a much smaller number of parameters? So actually, the culprit, the key effect of this second descent was realized in this nice paper by Neil. I mean, what they realized is that when you increase the number of parameters in your model, you also lower the fluctuations that are induced by initialization, right? So when you train a network, it remembers where it started. But if you have many, many parameters, this memory becomes vanishingly small. And they had observed this effect. So what we did as physicists is first to try to understand it, really quantify it. And so it's actually simple to quantify it. What we did is, instead of training a single network, we trained a family of networks, many of them, a number M of networks. And then we just average the predictor. We call it the Ensemble average predictor. And then what you can do is measure the norm, the distance between individual networks and the mean network. And we define a norm for that. It doesn't really matter what we choose, but for example, it could be uniform on some test set. And what we find is shown here. So this is a square fluctuation around the mean as a function of number of parameters. And what we found is actually a beautiful power law on like 3 decades. And those fluctuations were going like the number of parameters to the power -1/4. Okay, so I will come back to why it's this exponent later on. But first, let's assume it's the case. So first, how can I prove you in a simple experiment that this effect is really responsible for this second descent? And actually, it turned out to be quite simple. What I can do, so again, the blue curve is the test error as a function of the number of parameters. And for each number of parameters, we train 20 networks. That's why you have 20 points here. But again, what you can do is look at the mean predictor, Fn bar, and look at the test error of that one. And this is the yellow curve here. So it's quite remarkable because it means that once you look at the ensemble average predictor, this second descent is just completely gone. So it means 2 things. It means that really the slow improvement of test errors that you get is really about reducing the fluctuation induced by initialization. What it's also saying is that you can get a very good tester with a much smaller number of parameters. So this is a log scale that you see here, if you average your networks. And here, for example, it's average on 20 networks. And studying systematically the advantage of ensembling like that, we did it. And then the Google Brain team also has some recent paper on that. So it's true for CNN and for many architectures. So then once you realize that, how do we explain, we want to understand the sort of improvement in test errors, the difference between this yellow curve and this blue curve. If we were doing regression and if we were dealing with a square loss, it would be immediately would get that this difference in test errors, the cost of fluctuation, is just quadratic in the fluctuation, and so should go like 1 over square root of n. So with natural assumption, including the fact that the test error should be a smooth function of the boundary decision. If you have a predictor, it defines the boundary decision. We argue essentially that we should also get a square law for classification. And empirically, it works very well. So if you look at the difference between those two curves as a function of number of parameters, that would predict that it should go like 1 over square root of n. And indeed, that seems to be the case. In a log-log plot, you see a -1/2 slope. Okay, so that says that this second descent is due to this fluctuation. Now, can we understand why this fluctuation induced by initialization goes like n to the -1/4? And to do that, we need to think about what happens asymptotically when really the number of parameters goes to infinity. So first, what was understood already 20 years ago and also worked out more precisely for deep network recently is how deep nets propagate information at initialization. Okay, and what was found is that actually if you do an initialization of the weights where the weights are some Gaussian values divided by the square root of the width, then the limit is non-trivial. And you can obtain it just by making good use of the central limit theorem. You will find then that the neuron's preactivation is over the 1 and the output is also over the 1. Actually, it becomes a Gaussian process in the limit of infinite width, and you can compute its covariance f of x prime and so on. So that was known for some time. And the more recent result that was already discussed yesterday from my colleagues at EPFL is this notion that in this limit, not only propagation at initialization is simple, but also training becomes much simpler. And so their key insights, geometrically, if you think about the space of function, and this manifold in blue would be the function that you can probe by changing the weights. What you expect in general is that the function you're learning is a very nonlinear, depends very nonlinearly on the weights. So as you move along those manifolds, the gradients df over d omega, where omega is some weight, should vary. What they understood is that in this limit where the width goes to infinity, actually these manifolds become flat. So you can change the function a lot by something over the 1 while keeping the gradient fixed. So where does this miracle come from? Well, the key idea is that of, if you want, then it was later coined lazy training, but in physics we'd call it an interference effect if you want. When you have many neurons, small, tiny changes of weight can change the output a lot. They interfere positively if you want. But when you look at the gradient, the derivative, you don't have this positive interference. And so very tiny change of weight don't change those gradients. So at the end, what you get is that in this limit, the function f depends linearly on the weights. And that means that you're essentially dealing with the kernel method. And they could, and so what it means that the change of your function in time follows an equation like that, where theta is what they call the neural tangent kernel. And it means that although you have a very large number of parameters, the dynamic is stuck in a vector space of dimension p of functions. So what we did with them is to think about what happens when you are at finite end, not infinite. So at infinite end, you have this equation, but at finite end, you have two problems coming in. This kernel now will depend on initialization, and it will also vary in time. And so what we found in the data is that the dominant effect is really the fluctuation at initialization. And you can look at how to write the kernel and do a simple central limit argument to understand that at initialization, this kernel will have fluctuation and that they will go like 1/2 the square root of the width, like n⁻⁻⁴. And so when you train the network, if you have fluctuation of the kernel, you will get those fluctuations in the output. In fact, you can prove it immediately if the loss is a square loss, but we think it's much more general. So the fluctuation in the output just reflects the fluctuation of the kernel. So at the end, the key idea is that for this second descent, that you obtain a second descent because deep learning converges to a well-defined algorithm when n goes to infinity, but it converges in a noisy way. So as you increase n, you reduce the noise due to initialization. And then there have been more recent development on that, and they were discussed yesterday by Florent and others, looking at the random feature model. If you freeze the first layer of weights and you just learn the second layer, this argument I told you about would also hold true clearly in this framework. But in this framework, you can do theorems and really analytical calculation and work out in details how regularization would affect those double descent curves and so on. And here really the work that made the link between our approach and all this, this literature is the work of Florent and Giulio Biroli and others, which he discussed yesterday. So I'm not going to enter again into it, but at the end of the day, it's all consistent. Okay, so there is one aspect which is surprising, or is that I told you that the common belief is that deep learning works because you actually neurons evolve to respond to interesting features of the data. But in the infinite limit that I discussed here, the system becomes essentially a kernel method, and the pre-activation of neurons before and after training is essentially almost the same. Okay. So that would seem to suggest that, you know, I was discussing an asymptotic limit where features were not learned. And in fact, we do have evidence for features being learned. If you do the same protocol, so it's similar data as I showed you before, except that it's for a CNN acting on CIFAR. So the blue curve is actually the tester, and the yellow curve is again the Ensemble tester. And what you see clearly is that this yellow curve has a minimum which is deeper than its asymptotic value. So it works better at finite width than infinite width, which suggests that indeed in this case, presumably it works better because the neurons are learning features. What's a bit annoying here in terms of trying to do theory of that is that this minimum takes place at a finite width. And it's much easier to try to think and analyze what happens at infinite width. So can we have a limit, an infinite width limit, where neurons are still learning features? And in fact, it is the case. And in fact, it was understood even a few months before the neural tangent kernel paper was written, I think. And that's called the feature learning limit. And several groups came up with this idea more or less at the same time. And maybe I should also cite Lenaik Shiza and co-workers. And so the idea is very simple, and it's best understood for one hidden layer. And the only difference with what I told you so far is that instead of having a factor 1/√h, which you should have in the neural tangent kernel framework, you put a factor 1/h here. And so what it means is that at initialization, your output will actually not be over 1. It's going to be super small. It's going to vanish like 1/√h. And because the output is very small, and because you're trying to fit data and to make a margin of order 1, f has to become of order 1, you will have to change the weights a lot in that case. And because you change the weights a lot, the hidden neurons will actually learn to respond to different aspects of the data. And so if you want, features are learned. And this regime is called the rich regime, mean field, or feature learning regime. And it has some elegant analogy with liquid again, and I will quickly mention it because I think it's quite cute. So essentially, the key idea here is that if you have an output like that, and if you take h to infinity, you would really like to replace this sum by an integral. And then what will enter is a density. So neurons are characterized by two weights: the incoming weight, which is, you can think of it as a vector, and the outgoing weight for one hidden layer. And so you can write this output as a density of neurons which have such parameters. And here is just the effect of such a neuron. And then you can write dynamics directly on this density. And what you obtain is what you would obtain in physics, that the change of density is minus the divergence of the flux. The flux obviously is proportional to the density of neurons, and then there is a force, a gradient of a potential. And in general, this potential would depend on position, so the weights, and also on the density itself. And that's exactly what you would have if you were dealing with a liquid of interacting particles. If this depends on rho, it means you have interacting particles. And Eric was kind enough to send me this movie, which is actually not a movie of a neural net, it's a movie of interacting particle, but it's just to give you the intuition that when you have plenty of particles, it's better to think of it as a density rather than tracking the position of all particles. So here for DeepNet, it means instead of tracking each weight, let's track the density of neurons. Okay, so that means that you have two ways to take the limit of infinite width. So how do you cross over from one regime to the other? Which one has more performance? Okay, and so to study that, also in deep nets, not restricting ourselves to one hidden layer, we use an idea that Lenaik, Shiza, and Bach introduced, and it's very simple. As a predictor, you will take the function f I introduced before, but now you multiply it by alpha tilde divided by square root of h. So if alpha tilde is of order 1, then when h goes to infinity, you will recover the feature learning regime. If alpha tilde is square root of h, you recover the framework developed in the neural tangent kernel case. But now you can really think of this as a parameter and have it take any value, okay? And that's what this phase diagram is about. That's for CIFAR 10. It's a fully connected net of depth 3. And what you see in the x-axis is actually the depth h. It's the width h. And you have this coefficient alpha tilde, which tells you if you have a large initialization of your function, in which case you would be more in the NTK regime, or a small initialization. And what you find is the following diagram, which is summarizing several aspects of what I discussed already. So first of all, you have a separation between what is black here is the region which is jammed, over-parameterized, where the loss does not go to 0. So here instead we'll be focusing on the colored region, which is the over-parameterized regime. But in the over-parameterized regime, you have two different regimes, the lazy and the features. And empirically, you can really distinguish the two, for example, by considering how the neural tangent kernel has evolved during training. So you can look at technically at the gram matrix. And this black line here is when the evolution of the kernel is norm is equal to the initial norm. This line here is when it's just 1% of it. So here you really start to be in the lazy training regime. Was down there, it's the opposite. So for that line here, the kernel in norm has increased by a factor 100. Okay, so it's a smooth crossover, unlike this jamming transition, which is a sharp transition. It's a smooth crossover between two different regimes. And what you see is that the crossover corresponds to a flat line, a constant alpha tilde in this diagram. And that's something that was shown by Shiza and Bach for one hidden layer, and we could extend it to deeper nets in this paper. Now I didn't tell you what were the colors, and the colors have to do with test error, but I will come back to that point later on. First, what I want to tell you is everything I told you about double descent, was it only true for the lazy training regime, or is it also true for the feature learning regime? And so what we find is that it's true in both cases. So we explore this phase diagram along the three lines. This is a green line, this is a red line, this is a blue line here. And each time we plot the test error. And we also plot the ensemble test error which we obtain by training 20 networks and averaging them. And what we find is that in all cases, essentially we find the same in the sense that we do see a peak and a second descent, and that this second descent is eliminated if you do ensemble averaging. So also in the feature learning regime, you have a double descent. And again, it's due to the fact that you have fluctuation induced by random initialization. So what you could ask is, how now I told you that there is some scaling asymptotic properties of fluctuations as you increase the width in the neural tangent kernel regime. How is it in the feature regime? And we find that it's the same. So delta F, or this variance, is the fluctuation induced by the random initialization of the weights. What you see in orange, blue is behind the orange, corresponds to large alpha tilde. So you're really deep in the NTK regime, the kernel regime, and we already discussed this exponent. But what you find is that in the feature regime, you do find the same power law essentially. So the fluctuations still go like 1/√h. And in fact, it's easy to understand because in this approach, you replace the sum by an integral. So if you want, the network is a sort of Monte Carlo estimate of this integral. And by simple central limit theorem argument, you expect that fluctuation at initialization at least should go like 1/√h. It's quite natural that even after training, those fluctuations should still be there. And in fact, it was proven recently by Eric van den Eyden and Joao Bruna in a paper last year. So essentially, the message is that the second descent in both regimes, both the feature regime and the lazy training regime, in both cases, it's the same explanation. You go to a well-defined algorithm and you eliminate noise induced by random initialization. Okay, so I'm sort of done in terms of discussing of the second descent. Now the next question is really thinking about those asymptotic algorithms that seem to perform very well. So this the largest width you can obtain. You have two regimes depending on how you actually initialize the network, this alpha tilde. And you can ask, what about the performance of those two regimes? Which one works best? And here we actually find a surprising result. So what we find, and others found the same, is that if you look at more modern architecture, well, then you, for example, CNNs, you do find what you expect. On a variety of data, we find that the CNNs actually do perform better when they learn features. That is so this is a tester, you want it to be small, and it's small for small initialization. This is a feature learning regime. What is perhaps counterintuitive is that for very primitive architecture in gradient descent, and we study, various data sets, we find consistently that in that case, and it's independent of depth, one hidden layer or 5 hidden layers or whatever, we find then that almost always, we find that actually the lazy training regime dominates for those benchmark data set on images. So for those primitive architecture, it's not so good to learn features after all. So another interesting aspect is that when it is useful to learn features, then we do see that the gap between the two regimes in tester grows with the size of the training set. So those are learning curves showing in a log-log plot the tester as a function of the size of the training set. And you see for a CNN working on CIFAR, you see that actually the learning exponent, you have a faster decrease of the tester in the feature regime than in the lazy regime. Okay, so those are the facts. And now, what about understanding? So I would say that actually those facts we don't understand. We don't currently understand why fully connected nets don't work better in the feature learning regime. But let me mention one direction where the literature has been growing in the last year. And it's one case where it's clear that for one hidden layer network, it can be much better to work in the feature learning regime than in the kernel regime. And that's a case where data are very anisotropic. So think about the input X as having two sets of coordinates, orthogonal space and parallel space. And only the parallel space is informative. So the label only depends on those coordinates. In fact, the talk of Florent yesterday, his last model was looking at a very similar case, but there are many papers looking at this class of models. What it would mean for an image is that maybe on the edge of an image, you have pixels that vary but are unrelated to the task. And what's found in this literature is that actually, if you have this structure on the data, for fully connected nets, if you are in the feature learning regime, you can actually understand and perform much better, understand that there is this anisotropy, and essentially work in the good space and become insensitive to this orthogonal space. Whereas isotropic kernels, such as the neural tangent kernels that you obtain at initialization, and that remains the same in the lazy training regime, they don't understand, if you want, that there is this structure, and so they can perform much less well. Actually, that's something that we also looked at in a simple specific model that fall into this class, and we could show that the test error indeed was having a training curve exponent which was better in the feature regime than in the lazy training regime, and in this simple model, we have a prediction for those exponents that actually seems to work. But the problem with this literature, I would say, with these ideas is that, again, I told you that this is considering fully connected nets, typically one hidden layer. And I told you that for real data, for benchmark of images, at least, they work better, this architecture, in the lazy training regime. So that suggests that this kind of anisotropic symmetry in the data may be there, but it's not too important actually to learn images. And so I would like to conclude this talk with some ongoing work that actually we're about to submit, which is trying to think about, yes, what would be the other invariants that are important for real images. And there has been a very elegant proposition already 10 years old by Mala and Brunner, which is that maybe actually deep learning works because it understands, because there are lots of invariants, and the invariants would be that if you show a cat, for example, like this cat, if you do a smooth transformation of the cat, a diffeomorphism, it's still a cat to you. And because the space of diffeomorphism is large, maybe if the network can realize that, it can essentially reduce the dimension a lot. So it's a very elegant idea, but if you look in terms of empirical observation, it's not really supported by data. So what people have done in the field is looking at sort of cut and paste approach, where you take one part of the image and you move it, and you look how the trained network, how it's stable for such transformation. And what you find is that actually for such transformations, the output can change a lot. But what we found is that those are very special cases. Actually, they are not really diffeomorphism if you cut and paste part of the image. So what we really wanted to revisit those ideas and define typical diffeomorphism. And to define typical diffeomorphism, what we did is to introduce a maximal entropy model for diffeomorphism. So essentially, we look at a uniform distribution on diffeomorphism that have the same norm. And the norm is the usual norm that characterize how deformed is the image. In a canonical ensemble, it boils down to introducing a temperature. And here I show you essentially what we are doing. This is the image of a cat. And then when we crank up the temperature, we have stronger and stronger diffeomorphisms that deform more and more the image. And the question we ask is, if you look at modern architecture, did they learn to become, invariant, to be very stable with respect to such transformations? And here is how we quantify things. So what turned out to be universal is not the stability to diffeomorphism, but what we call the relative stability. So think about an image. So this is input space. This is a black image. It's your image from the cat. And then you can think of deforming this image using diffeomorphism. This is an example here. And around those data, diffeomorphism send you in some manifold around you. So you can study how your trained network, how it is sensitive to such deformation. And here we average on all our ensemble of diffeo and on the training data. What we find is that it's important to look at relative stability and to compare this with stability with, random perturbations. That would be this dog here in red. And this is the denominator in this quantity. So RF characterizes the relative stability to diffeo transformation with respect to any transformation. And so what we studied are state-of-the-art networks proposed in the last 20 years. And what we found for them, so we take them pre-trained, and we can also look at them at initialization. And what we find is that at initialization, R is over the 1. So at initialization, those networks, they don't really distinguish diffeo direction from random direction. But after training, we find that this quantity RF can decrease a lot, and it does decrease very much so in the most modern architecture. So what you see in this plot is a tester as a function of this relative stability to diffeo RF. And what you see here are 15 state-of-the-art, preview state-of-the-art networks. So these are all networks fully connected. Here you see early CNNs like LeNet, AlexNet, and here are really the modern ones. And you see that the modern ones, actually, they manage to become much less sensitive to diffeo and relative terms, like you have 3 orders of magnitude. But clearly, what's most remarkable in this plot is that the degree of correlation. So the tester for all those state-of-the-art networks seems to be extremely correlated to this quantity RF. So indeed, it supports the idea that learning this relative stability is key to the success of deep learning. Okay, so let me conclude. So the main point of this talk is first that if you increase the number of parameters in your model, you will undergo a sharp transition that marks the entry toward an underparameterized regime. And once you're in the underparameterized regime, you're not stuck in bad minima. And the second point is that past this regime, you have the second descent. The tester diminishes as you increase the number of parameters. And essentially, it's simply due to the fact that you're converging to a well-defined algorithm and you're getting rid of noise induced by initialization. And that puts forward the practical implication, which is the benefits of ensemble averaging. And then the last 2 points are more questions. There is no theory, even at the, I think, qualitative level. One empirical point is that if you look at what regime perform best, once you are in this overparameterized phase, you have two regimes. And what regime perform best seems to depend on the architecture. For modern architecture, it's a feature learning regime, but not for fully connected net, where yet most of the theory is contemplating. And the last point, and it's also raising more questions than answering, is a remarkable correlation between the test error and the relative stability to default. And it supports that indeed this idea of Mala and Brunner of deep learning working because you build this stability may be true. Okay, I'm done. I don't know how I did on time at all, but I'm done.
Excellent. Let's, yeah, great on time. Let's thank Matthieu. Really interesting. Yeah, really interesting talk. Lots of interesting things to think about in there. We do have time for questions, and there are 4 of them in the Q&A section of Zoom. Can you see those, Matthieu? If you just go down to the bottom, there'll be a Q&A bubble, and there's the red number 4. Do you see that at the bottom of your screen?
All right. Yes.
Yeah, and if you do see it, then better if you could reread the question if you like, and just these all look really interesting, so we have time to address hopefully all 4 of these.
All right. So the first question was, does the fluctuations due to initialization also decrease for neural nets with fixed width and increasing depth? And that's, so what happens when you change depth, which I precisely avoid to talk about. So there is also a vast literature on that. And the idea is that if you look at very large, very deep networks, then you again have sort of 2 phases that show up, if you don't use batch norm at least. And you look at initialization, say you have a sort of chaotic regime where even if 2 data points x and x prime are close to each other, f of x and f of x primes are going to be decorrelated. And you have another regime where it's the other way around, you lose all information. So whatever x and x prime, it's the same output that you get at the end. So I don't know the specific answer to the question that was raised, but I would think of it in terms of those 2 regimes. But it's a good question. But there is some literature on that, but it's not fresh into my mind now.
And if I can just interrupt, Matthieu, I forgot that in fact these 4 people have been had their audio enabled. So sorry to Kung Ching, but if Jose would like to ask his question, then Matthieu can respond.
Hello, Matthieu. Great talk. Yes, a very quick question about the mean field regime. Is there any way to generalize the mean field regime for multilayer neural network? I know that there are some work, like the work of Roberto Oliveira, the work of Sirillano, but in the case of Sirillano, he's sending each of the layer 1 by 1 to infinity, and it's not clear that this is the way to go. In the case of Roberto Oliveira, he's frozen the input and the output, given that it's a different scale in which goes to infinity. But at this point, if you compare where it's a multi-layer neural network with a shallow neural network, it's very clear in shallow neural network how to send it to infinity, but in multi-layer neural network, it's not clear at all how even try to send it to infinity different layers. Is there any unified approach in this case?
Okay, so this is a very active topic of research. It's true that in our experiment, we just do it, you know, we just do it. And but in terms of understanding what is this limiting algorithm when you take the infinite width for a deep net, even if it's a simple fully connected net, it is still debated. So there are several approaches to that. There is this tensor approach, and now I don't remember the name of the authors, and so on. But I think there is much more to do in terms of having a description that give us more intuition about really what's going on. So I think I don't think we have a very good answer to that problem yet. Also,
Okay,
I think for
yeah.
So sorry for a negative answer, but I mean, yeah, there are many works on this topic, but I don't think it's settled yet. Maybe what I could add is, in terms of performance, what we see empirically is that it's not true. If you have a fully connected architecture, depth actually, even in the feature learning regime, does not really help you. So I think really having the CNN is really fundamental there in terms of achieving good performance. Yes.
Okay, let's move on. We still have time to have more questions. Daniel had a question.
Hi, Matthew. Can you hear me?
Yeah, I can.
Okay, thanks for the very interesting talk. So I had a question about the effect you saw with ensembles, and I believe you said that you observed this in the linear regression case as well. And what I'm curious about.
No, so we didn't look at linear regression.
Okay.
So I was more referring to the talk of Florent that was looking at it for the random feature model.
Oh, I see.
Yes, where those arguments about, you know, converging to well-defined kernel, like one of the square root of h is sort of trivial in that case. I mean.
Okay, no, that actually answers my question, because my question was where the source of randomness is in the ensemble. So thanks.
Okay, thanks, Daniel. We only have time for one more question. So maybe, Matthew, you could respond to Amir's question by typing right after. But Spencer, if you'd like to ask your question, that'd be great. Maybe you're on mute.
Spencer Frey, should I?
Yeah, you could just read the question unless.
How does relative stability to DFO relates to adversarial robustness and stability to L2 infinity perturbation of the input? Is it possible that if one does adversarial training, the stability to diffeomorphism would improve? And those are excellent questions. And it's true that our work, we look at the stability to random direction and to diffeo, and it brings us into contact with that literature on adversarial training, but we want to explore it, but we've not explored so much yet, so I won't have a deep answer to that question. But yet, yes, so what it means is that it becomes very robust to, if you take an image and you look at the diffeo transformation of that along those directions, it's actually becoming very robust and stable. On random direction, actually, we tend to see that as you train, so you know we define this relative index of stability, the direction of DFO divided by random direction. Stability to random direction is actually getting worse and worse as you train, because you're trying to fit more and more points, and so the function is becoming rougher and rougher. We're actually studying how this sensitivity to noise depends on the spectral structure of the noise and so on. So there are plenty of questions that will connect to indeed adversarial training, but we've not done this connection yet.
Okay, I think we're going to have to stop here. Matthew, it'd be great though if you could just hit type answer on Amir's question there after your talk. But let's thank Matthew again for a really thought-provoking presentation. And yeah, really, really cool.